Thank you, Mika, for the introduction. So hello again from my side. And in this first part, I would like to briefly present who we are and the basic idea of the project. So, as Mika said, we have an acronym, Innocrosslam, and what does this acronym actually mean? It's Innovative Solutions for Cross-Laminated Timber Structures. So I will just repeat what Mika described, because these are our main aims of the project: to increase even further the really competitive CLT as a versatile engineering product by dealing with demanding design situations which are not covered by design or guidelines of today or in the near future. And in parallel, we were further developing a multifunctional use of CLT as an integrated part of heating and ventilation system. So who we are? We were five full project partners. Us from Slovenia as the leading partner, and then from Lund University in Sweden, from Vienna University of Technology in Austria, Technical University of Munich in Germany, and University of Navarra in Spain. However, we have also several, in addition to research partners, we have several associated partners which represent the industry, architects, and civil engineers. At this point, I would really like to thank and acknowledge all my co-workers. Since the COVID-19 pandemic affected also our project, it was only due to motivation of my colleagues and that we were able to adapt, and in my opinion, and hopefully also yours, that our project was very successful. So with this last slide, I would like to show in this simple image the content of our project and the relation between our work packages. So these specific design situations that we were dealing were CLT deep beams, point supports, then CLT with openings, as described in the introduction, the thermally activated and multifunctional CLT panels, then CLT connections, lateral stability of CLT structures, and especially in this case the seismic safety. And with this we were also focusing on inside of the material behavior and stress singularities. So I invited on stage three professors to discuss the motivation on why we applied our project. And first it's Professor Eric Serrano from Lund University. He's the head of Department of Construction Sciences, which he was also one of the initiators of the project. Then Professor Philip Ditch from Karlsruhe University of Technology. He was leading a cost action from research to practice of timber structures. And then Professor Stefan Winter from Technical University of Munich. He is the chairman of the Eurocode, new Eurocode 5, and was the one that directed our research, which then was helpful to be more related to the practice. And in this image, I have a tree with a word cloud. So with the topics that were keywords of our project. So you can see the ones bigger, which I found the most important for our project. But to discuss with the professors. So we have a question because there are hundreds of research projects in Europe alone. So Eric, why did you feel or think it was important to propose another project called Innocrosslam?
Well, it was said already related to the motivation, but as I saw it then when we decided to write an application for this call, somehow at that point, I mean, CLT has been around. It's a fairly new material, meaning only about 30 years, 25. So in that sense, it's well established, at least the first or possibly second generation of materials. But going beyond that, we saw lack of knowledge and also lack of, I would say, approaches in research and characterization methods, modeling methods, treating this with more theoretically sound-based approaches. That was my driving force, and I think we saw from that point of view really some knowledge gaps to get beyond very standardized design situations, basically.
And if you allow me to add, my addition would have two parts. The first part is the cost action FP1402, which I had the chance to lead until 2018, and we ended that cost action with a two-day workshop. And in that two-day workshop, 60 experts discussed what are future questions for the timber sector, for timber construction. And actually quite a lot of these questions circled around the future of massive timber construction. And the second part of the answer is the work in Project Team 1, in which we wrote the rules for the design of CLT for the future generation of Eurocode 5. And during that work, we came to the conclusion that for 85% of the design cases, we have good solutions. But we miss this gap of maybe 15%. And this gap is important because it still appears in most of the buildings. And to find design approaches which are harmonized so that not every office would have to find their own individual solution, that was the second driving force for me personally.
Anything to add?
Exactly the same opinion. In my role as a Czech engineer in practice, I see a number of cases from this 15%, probably it's 20%, not solved up to now, but they are appearing on building sites, and then people are looking at it and then, okay, we can solve it this way or probably this way, and a lot of discussions around sometimes, points which could be solved, of course. And in my role as a chairman of Eurocode 5, of course, I would like to support more European technical harmonization. And we know that there is a lack, especially in the field of CLT. We don't have a harmonized European standard at the moment available for CLT. Fortunately, we will become a lot more common design for CLT in the new Eurocode draft or based on the new Eurocode draft. But these open questions, these are the drivers, of course.
Yeah, so we covered the first one, harmonization. But maybe you all as researchers have a personal motivation why to join the project or why to have this European project. So
you mean topic-wise?
Yes.
Well, fracture mechanics is an interest of mine. But that's more or less just a symptom, I would say. I mean, what I said before is I'm very much interested in introducing more design methods based on let's say a sound or at least sounder theoretical basis than some more empirical approaches. So that's my driving force, and in my case in particular the use of some specific modeling approaches related to fracture mechanics. But those relates then to holes and notches and things like this. Yeah.
Mine would be holes in a different way, CLT with cavities, or the thermal activation of CLT elements. The proof of concept of this had been done before by a colleague of ours at TUM, but it was not fit for use in practice. And so that driving force was to bring this as close as possible towards practical application.
The transition, yes.
resource efficiency. And this is very close to CLT with scaffolds, for example. I think, or what we can see, even in this building, CLT is a mass timber product. But also we are using a sustainable material. Also, these resources are limited, of course, and therefore we have to think about resource efficiency also in the sector of CLT. And by the way, being part of a European project, it's always nice to talk with the European partners and to leave the own home and discuss with all the others which are involved in such a project.
Okay, so we covered many of the keywords from the tree, but still maybe the last question would cover even more. So our project received a lot of support from the industry and practice. And what is, in your opinion, the reason that we received this support, so this large support?
I see, going back or pointing back again to what has already been said, I think the 10, 15 or 20% of the design situations, that I think there is a need, somehow a frustration, perhaps, for the everyday practicing engineer. I would also like to highlight the ambition we had in starting with this and trying to follow through, which has of course been difficult with the pandemic situation, to involve also architects and in our project to help us define or find the everyday challenges not being able to easily solve today. I think this has meant that they've felt really involved and being able to contribute.
Exactly, and the main reason is that 20% of missing issues are consuming 80% of the time in the design of a project.
And just as a final addition, this idea of thermally activating CLT elements, industry said, hey, cool idea, but what about? And to answer this what about, I think they were interested in us trying to do so.
Okay, thank you, professors. And I would like to continue with this, how we engaged the industry. And because this was an important aspect of our project. And I will invite Martin on stage.
Okay, thank you, Boris, and yeah, good morning, good morgen, or bonjour, buenos dias, however you would say it. My name is Martin Schenk. I'm a research associate at the Technical University of Munich, and I might introduce you now and also put this discussion now into values, basically into numbers, to the work package Structural Design, which is led by Professor José Manuel Cabrero and Pablo González Serna, both from the University of Navarra in Spain. So the background is now very clear. The relatively young material CLT barely made its way into the European design standards, the Eurocode of the first generation. But it will get implemented further into the second generation. For us, the question remained, is this everything that we have now or that we see every day on site, or as we saw it now the last days within this building? To investigate that further, we started with a digital questionnaire. We distributed it in 2020 to a target group of designers, constructors, and researchers. We distributed 48 questions, and at the cutoff date, we received 141 replies from participants from more than 20 countries. We received information about the experience of the participants on CLT construction, on their general design methods, on CLT and their finite element software, and also to complex design situations, like, for instance, joints and connections or seismic design. So, as we have seen, Eurocode 5 barely mentions CLT, and that can be seen here from this slide as well. So, on the left-hand side, you see all the literature that has been indicated during this survey, and in blue you see highlighted official standard documentations. The others are mainly research papers or CLT handbooks. On the right-hand side, you can see the picture gets more homogeneous when we have a look to the documentation of product parameters. So highlighted in blue, you can see EN 16351, which is the product standard, or, for instance, ETAs based on an EAD distributed disseminated by IOTA. For the calculation of CLT, many procedures exist. You could simply conclude them or summarize them under hand calculations and software solutions. And as you can see here from this slide, no best practice solution exists. All of the designers, constructors, and researchers apply some kind of a combination of solutions, and what very clear, what can be seen very clearly here, software solutions play an important role. But when asking our engineers, do you verify the output of your software? 20% said no. Nowadays, that's quite fine, right? Our FE software is really good, and that's fine for us. No, of course not. This is a high barriers are a high risk of failure, as you use every day your autocorrect mode for writing messages with the mobile phones, although the FE software could lead us wrong. This gets even more important, or more. This is even more important when you have a look at this slide now. We also ask some specific question about the mechanical modeling, for instance. On the right-hand side, you can see the influence of pulling a rope of an elastic material and how the cross-section would change. And on the left-hand side, you see a question about the value which describes this correlation. And around nearly half of the participants said that they don't know which value would be assumed in their software. Now changing to the complex design situations, well, we ask about several situations. You can see on the, let me try this. Oh, this is small, but you can see here deep beams with holes, cantilevers. You can also see here asymmetrical layups, openings in floors, openings in walls, and point supports and concentrated loads. So, and as you can see here on the slide, the concentrated loads and point supports were indicated as the most difficult design situations next to the openings in walls and floors. And yeah, the engineers very clearly stated what is the problem about these design situations. It's the missing design, missing or incomplete design concepts. We also asked about the connections, and yesterday that question was raised also when we were having this tour in the building. How do you assume the stiffness of those connections? And well, most of the engineers apply springs. But when we ask about where do you get the values for those stiffnesses, the scatter of indicated literature was even wider than for the structural design. Coming to the seismic design, around 50%, 40% of our engineers have ever applied a seismic design in CLT. And also there, they indicated missing standard solutions as a reason, or the main reason, for not applying CLT further in seismically active areas. That has been the digital questionnaire. Now, in addition, we made some face-to-face interviews in times of Corona, of course, online. with selected experts, 5 consulting engineers, 3 CLT manufacturers. And there we ask about the preliminary design for some complex design situations. We ask also about the connections and the structural and mechanical modeling. You can see here one of the pictures, for instance, that we showed, and we asked them one of the question, for which ratio L, the span, to H, the height of a wall, would you assume a linear bending stress distribution? And there you can see, okay, there's some kind of, let's say, a tendency to a value, L to H, 4:1. Other engineers apply directly the numerical methods, so the FE software. But it's not always like that. Let's say that we receive a tendency to a single value. So having a look here to this picture that shows the openings in the floors, and yeah, the answers are quite different, as you can see there. So for instance, you have a ratio of the opening factor to the utilization factor, or you have a ratio between the opening size to the span. So let me draw some conclusions. There are definitely knowledge gaps with respect to some mechanical modeling, especially to the torsional stiffness of plates and banding and the Poisson's ratio. The most challenging design situations for engineers in practice seem to be the point supports and concentrated loads, the openings in walls and floors, and joints and connections. Beyond the ultimate limit state, engineers identified as very problematic the vibrations, durability, and execution. And finally, given reasons for that are the missing incomplete design guidelines and the lack of education and training. Yeah. So that has been the kick-off for the work of all of our work packages. And now let's see, having a look, how we could contribute to solve these problems.
Okay, so since José Manuel Cabrera, professor, is not able to be here, he prepared a video.
Hi, Celeste. This is Professor Cabrera from Pamplona, Spain, speaking. It's a pity I couldn't make it there, but here's my video to contribute to your wonderful meeting today. So as you saw in Innocrosslam, we're talking about cross-laminated timber, comprised by perpendicular layers of timber. Timber is already a complicated material from an engineering point of view. When you add this additional complexity, you get even more complex problems. So how do people in practice deal with this? That was one of the main issues that we care about in this project. So most of the people use either practice-oriented software or CLT-oriented software. I mean, quite dedicated solutions for this. However, when they verify their approaches, when they verify the models, they make quite a lot of use of hand calculations. So such a complicated material is dealt eventually with the use of very rough numbers. When we talk about modeling, in the case of CLT buildings, we are talking about modeling vertical components, walls, horizontal components such as floors, and in both of them we have openings and all of them are connected. So those are the main issues. There's an additional issue in the case of CLT buildings, which is that sometimes these CLT walls are responsible for the lateral stability of the building as well. So that's an additional problem to be solved by means of modeling. How is this lateral response of the building actually? So it's a complex material in which we need to take care on these plates of the bending response, the shear deformation, the translation, and the rotation. And as you see in the picture below, there's also an influence, a high influence in the load transfer and in the lateral response in the way we connect those panels among themselves. When we talked about the types of models, we can go from the shell models, which are typically used, in which we model the whole geometry as means of planar elements, and we can simplify that by means of beam elements, from being religious, quite complicated, to more simple, and even at a later stage, to a very simple beam model. So each model, in a way, will allow us to make different types of modeling, and those shell models are typically the ones used by practice when accomplishing the model of the whole building. But when we're talking about cross-laminated timber and having a wall like this with holes on it, with windows on it, there are different constructional approaches. We may divide the wall in these panels, or we may divide the walls in this alternative way. These two ways of building the actual wall actually have a different structural response, and we need to make sure of that. That's why we made a master thesis in collaboration with our Swedish partner from Lund. So of course there's a difference on the lateral deformation, as you see here. The more fragmented the wall is, the more translation that we may experience. But not only that, we need higher number of connections, but also those divisions produce a different load transfer mechanism. As you see here, the building on the right requires a higher load capacity of the connection in the corner than does the building on the left. So the constructional approach has a lot to do with the structural response and the structural demand. It's sometimes a problem of divisions. Divisions have to do with the number of connections we use, and the number of connections and their location strongly affect the response of the building. And in the case of CLT buildings, there are many connections. So connections are a key issue when modeling CLT buildings. That's why we ask the practitioners, what do you do in practice? Most of them use semi-rigid approaches by means of sprint model and getting the documentation from the producer. So that's why we made a master thesis again, where we model many different combinations of connections, taking into account not only the tensile stiffness, but also what type of compression response we're having, what type of shear transfer we're having, and what type of rotational response we're having. As you see here, many different combinations and in a very detailed way, in a very precise way. This gives rise to the problem that practitioners already saw. They saw that there was a huge potential for improvement in connection design. They saw that there were many issues that they were not solving. That's why we made such a detailed approach. The main conclusion was you could make use of simple pin connections as a simplification when you're not relying on the CLT system itself for the lateral support, or when the lateral loads are not big. Of course, this is not the right way to model the building when you're dealing with strong winds or seismic design. In conclusion, when modeling CLT buildings, you need to have some very early design decisions which actually are going to influence your model. You need to decide which type of construction type you're going to make, either balloon or platform frame-like construction, how you're going to divide the wall, how you're going to divide those holes and how you're going to produce them, how you're going to connect them, and how you're going to deal with the openings. All these are essential key points that you need to take into account in your model as soon as possible. When we work on these very detailed models of the building, we found out some modeling problems already, some numerical problems, as you see here, some stress concentration issues, and also when you're modeling holes in the walls or in the slabs. That's why we made some tests on holes in order to have a real picture of what's going on in a real CLT plate with holes, and hopefully that's some of the answers that we will find out in the next presentations, because we dealt not only with these stress concentrations problems, we've also covered what happens with point support loads, which also produce stress concentrations, and especially what happens with the moisture transfer, which was a very delicate matter in our case, trying to make use of this multifunctional CLT plate that you will see following presentations. And that's all. Thank you very much for your attention. Hope to see you in person the next time.
Thank you. Well, Professor Cabrera already announced the presentation that follows, which is dealing with the material itself. So please, Professor Fussel and Markus Lukačević from Technical University of Wien to continue.
Okay, it's a pleasure being here. Thank you, Boris. So within the last 10 minutes before lunch break, please follow me from the structural analysis to the wood component level. And we've learned today already that the outcome of structural analysis is only as good as the input, and the input needs to be gained at the wood and wood component level. And that's the motivation why we are focused on computational mechanics applied to, I hope I can switch the slides. No, I cannot. Oh, okay, now it works. We're focused on computational mechanics, and I will show you an overview of results computational mechanics applied to different wooden components. And we do that because we see a huge potential for simulations to be a useful extension to experimental investigations for essential 4 reasons. First, it provides a lot of information. We get stress, strain, deformation states in each point of our investigated structure. Second, it allows for extensive parameter studies in a very efficient way. And this comprehensive information is required to set up guidelines, standards, design rules for Eurocodes. Third, it makes certain investigations possible, especially ones where you have very large building components like 3-meter GLD beams, for example, which are not uncommon or will not be uncommon in the future. Or when you have extremely low loading times, like a moisture loading over several years. That's possible with simulations, and normally you then also have a lower cost compared to equivalent experimental tests. However, for all of you who do experiments, they will always be required and for validation purposes, and we believe that both needs to exist in parallel, and then we have the best effect to boost timber structures. So let's give you a couple of examples. With respect to, I will start with moisture safety because that's an increasingly important topic. And here you can see, for example, such a result from a numerical simulation, the moisture distribution along a path from the surface point to the interior of a cross-section over a couple of months. And you see the fluctuations of the moisture content on the surface point in the interior. It looks different for a GLT cross-section, and it looks different for a CLT. But just that you can see, you get a lot of information, the moisture content at each point in time too. So it's quite efficient and to do such simulations. You can also couple then these moisture simulations with mechanical simulations, as you can see here, and on the right side you can see it coupled with an extended finite element simulation where you can even predict the crack depth induced by moisture loading. And then we have done this for different cross sections, determined the correct depth, and compared the resulting values with assumptions from the Eurocode, for example. So you can also use then this huge amount of information to check whether your assumptions or design rules and guidelines in certain codes are on the conservative side or not, or whether they need to be improved or not. In this case, there are actually quite good assumptions in the Eurocode 5 with respect to correct depth. But we can go one step further and calculate such graphs, which are probably interesting for engineers, which give us a critical crack depth as a function of the moisture content reduction after installation, and also depending on the initial moisture content, so the moisture content at the time of installation. And you see huge differences between initial moisture content of 10% compared to 15%, so of critical crack depth you can expect in your wooden components. We've also looked at timber concrete composite floor systems. How large does the moisture content concentrations in certain points become? Are they critical or not? But more important, under normal indoor climate, how fast, how quickly do they decrease? And they decrease quite quickly, so they shouldn't become a problem. However, sealing of these end grain surfaces can significantly improve the moisture behavior. And finally, with respect to moisture, we have simulated such CLT experiments. They were put into water by a partner university, Teltec. And here on the right side, you can see then the data of 4 measurement points. In red, the average values, and in blue, the simulated ones. And with a little bit of calibration, not too much, we can see that we can reproduce the experimental data quite well. and which is great because now we have the possibility to actually investigate different cases which can arise, which are probably seen critically from engineers in timber industry or other industries, from the concrete industry. And if someone tells you that's critically, that's not possible to do in CLT, you can run a simulation and say, no, please prove me wrong, but we believe that's possible, for example. So that's the reason why we're doing this. And now I will give the floor to my colleague Markus, and he will show you another 4 examples.
Yes. So another question we try to look at is how to handle stress singularities and material variability caused by knots and fiber deviations. Yeah, so we invested actually quite a lot into the ability to realistically model failure mechanisms in such sections of wooden boards with knots. And we could show that by using very advanced methods like this phase field approach, you're actually able to simulate such very detailed fracture mechanics effects. So the idea is in the future to use such very detailed simulations to, for example, get more detailed effective properties for such sections of knots. And then you can get effective strength, effective fracture energy properties. And once you have such properties, you can, for example, use it in the simulation of glued laminated timber beams. So in such a beam, you can then divide the lamellas into sections with clear wood and knot sections. And each section has a different effective material property. And we could show that using such an approach, you can not just predict the load-bearing capacity quite realistically, but also the global failure mechanism. And this works not just for 4 lamellas, but for 10 lamellas. And quite recently, we are doing a large set of simulations with up to 100 lamellas, where we studied the size effect regarding to bending strength of glulam beams. Another task of ours was simulation of structural details. For example, answering the question, we already heard a lot about it, how can you consider the stiffness of connections more realistically? So here again, we use detailed nonlinear finite element simulations, for example, of this shear connection of CLT elements, and then in the next step of such CLT floor wall connections, but not just running these simulations, but we also try to derive then more simplified spring models, which in the next step can be used in engineering software. Just some other examples of our research within this project was, for example, simulation of such point-supported CLT elements, where we are also able to predict all possible failure mechanisms realistically. And once you have such a model, you can easily perform parameter studies, different dimensions, ratios, different loading combinations. So something which is not too easy if you do it by experiments. They're too expensive and you need extensive programs. On the right-hand side, you see another example of a timber concrete composite element, here with notches as shear connections. And here we could show that something which was tried with experiments, that it's not too easy to predict this load-bearing capacity with small-scale specimens, because we saw in our simulations that actually the load transfer mechanisms and also failure mechanisms were quite differently. Yeah? So something you can study in detail with such simulations. And as a very last example, I want to show you simulations of screw press gluing of, in this case, a CLT and a GLT member. Here you can see, for example, that if you consider the stiffness of the glue itself, you can reduce the stress gradients right next to the screw, something which is maybe more realistic, which you can also experience in experiments. And with this result, I think we could add a little bit to the ongoing discussion, what is now the necessary distance of such screws in actual timber codes. Yeah, and with this is the end of our part, and I guess now we have a lunch break.
Yeah. Okay, so to warm you up after lunch, let's go to our core activity, so to the innovative product we were developing. And for this presentation, we have again Philip on stage and Matthias from Technical University of Munich. Please.
Yeah. Thanks. Thank you very much, Boris. Thank you very much, Mika. Always a challenge to attract your attention after a good lunch, after all the inspirational talks you have had in the last hours. Maybe to make it a little bit more interesting for you, we increase the level of difficulty by adding one function to CLT. What am I talking about? I am talking about the old idea of thermally activating structural elements and transferring that idea to the product we know well, which is CLT. 7 years ago, our former colleague Klaus Mindrup made the proof of concept. He would circulate conditioned air, warm or cold air, in the CLT element. Of course, circulating water would be more efficient, but water and wood, we know, has some difficulties, and this would involve placing tubes in the natural material, which is wood. Not only by simulations, but also by experiments, Klaus Mindrup could prove that when you use the second innermost layer of a CLT element, you would receive competitive results with respect to specific heat output of such an element when compared to the standard surface applications that are there on the markets today. The first idea did not work. That was obviously to thermally activate the center layer of this product. I can imagine you seeing this idea maybe for the first time. You have many questions in the case, yes, but what if, what about? And the main objective in this work package was to answer the most important of these questions. And this was the task of Matthias Arnold. So please, Matthias, could you introduce us to some of those important questions that had to be answered?
Thank you, Philip. So the 7 essential requirements for construction products are giving us the questions to be answered. So if we look at this small sample of multifunctional CLT, then it gets obvious that the cavities are influencing the mechanical properties, and the asymmetric layup may cause an overall deformation behavior, leading to an overall curvature in the element due to the asymmetric moisture profile over the cross-section. Also, we have to think about the safety in case of fire. What is if inside the channels a cavity fire is burning? How can we extinguish it, and how does it influence the overall fire resistance?
Okay, so now we know the questions, but could you introduce us a little bit more to the product? How could this product actually look like?
For our investigations, we were able to produce and to develop 5 different series of multifunctional CLT, which you can see here are the basic CLT elements, which were produced by Pfeiffer Timber GmbH. And adding to these elements, Lignotrend, a German company, was able to add the functional layers and the airtight front layer to the non-edge glued basic CLT elements.
Okay, these are nice drawings, but were our partners actually able to produce this on an industrial scale?
Yeah, we were worried about, due to the high number of test series we needed for our investigations, we were worried to find a partner who is able to produce this on industrial scale, but Lignotrend in the past and currently is always producing mass timber elements featuring channels, so they were able to produce it and to integrate it within their standardized production processes without problems.
Okay. Which means we could come back to the questions characterizing that material, and starting with essential requirement number 1, which is the mechanical properties. What kind of questions did you have to answer in that aspect?
When it comes to mechanical resistance and stability, we try to investigate as many stiffness and strength properties as possible. Therefore, we started with the determination of the compression strength and stiffness, and this led us to the determination of the buckling loads, for example. I will show you a short clip of the investigations of these wall elements with 3 meters of length. Now we hear the cracking. And here's the quite brittle failure for the multifunctional CLT series. Per meter wall lengths up to 0.7 meganewton were achieved in reference to the standard 5-layered CLT non-edge glued, which was 1 meganewton. So it was a bit less, but overall quite good results. Then we did in-plane shear testings. Most of the specimens had a failure in net shear due to the lack of edge gluing and in break-off of the functional layers. On the right side, you can see a unique test setup for the determination of biaxial bending for torsional stiffness properties. This test up was also used for investigations on diagonal layer arrangement within CLT, which is highly relevant for example, point-supported slabs, just to mention, if you haven't read our latest publication in Construction Building Materials. But to answer your question, back to multifunctional CLT, the compression strength and stiffness are at the same level, but what is really lower is the in-plane shear strength and stiffness and the buckling loads.
Mm-hmm. Okay, so that means we do have now values for the load-bearing function, but we know now we want to circulate cold or warm air in this element, and warm air will withdraw moisture from the timber element. What kind of influence does this have on your wall elements?
Yeah, like you introduced, during the heating and cooling processes, temperatures between 15 and 45 degrees occur in the channels, which of course leads to an asymmetric moisture profile over the cross-section, which is always switching from side to side due to the heating or cooling mode you're in. And so we figured out the deformation behavior, and we put 4 specimens of each series into a climate chamber in order to investigate the overall curvature.
And what were the results of this investigation?
So if we look at this, on the right side, you can see our measurements in different depths. We measured the moisture content over the cross-section by means of permanent ram-in electrodes. And on the upper charts, you see the heating and cooling phases we went through, and on the lower charts, you see the moisture profile. And you can see at the beginning of the heating period, at 8th of August in 2020, there was a clear switch in the moisture profile, and this led to a switch of the overall curvature, which we measured by a measuring bar, which you can also see on the right side. So what have we learned? It is really important to use high quality solid wood panels for the front layer, which leads to a lower risk of cracking due to maybe in the assembly constrained deformation.
Mm-hmm. The most mentioned challenge by the colleagues that we talked to was actually the essential requirement number 2, safety in case of fire. That was a big question to be answered. Could you introduce us to some of the items that you had to cover?
Yeah, true. Safety in case of fire is one issue, and main issue we had to figure out what is happening, how is the fire resistance influence. So we tried to cover as many investigations as possible with our fire testing. So we measured time temperature curves, the mass burning rate, and the fire protection closer. And also we tried to figure out what is happening in case of a cavity fire.
Mm-hmm. And can you tell us about the influence of the cavities on the resistance?
So what we see here is the well-known time temperature curves behind each layer measured on a standard 5-layered CLT element, non-edge glued. Every one of you maybe knows this, and it's the burning, the fire load was following the ISO 834 standard fire curve. If we compare it now to a multifunctional series, then we see a clear reduction within the channels by 50 minutes of the overall fire resistance due to the slower burning rate.
Mm-hmm. Okay, a second possibility, of course, is fire inside the cavities. What kind of effect would this have?
Okay, let's remove the 01 series. Now, these are the time temperature curves for the multifunctional series, and now we have the fire event just inside the room, and what we add now additional is a specimen with cavity fire. How did we do it? We took the specimen and set it inwards into the oven to guarantee a burn-in and then circulating cavity fire in the elements. And what we see is that we are losing 10 more minutes of the overall fire resistance. And what we also investigated were chimney effects, but just to make it a clear statement, it's a reduction of 10 more minutes of the fire resistance.
Okay. So for me, this means actually that we can produce this product on an industrial scale. We do have numbers for mechanical resistance. We have some results on the fire resistance. which questions do we still need to answer, or which steps do we still need to take to really make this product ready for the market?
I mean, first of all, we have to extend the EAD towards CLT featuring cavities, for example. Also towards elements featuring diagonal layer arrangement and things like this. And the next step is, and what we are currently working on is to get the requirement done, the sound insulation, how is the sound insulation influenced by the cavities. So this is what we are working on right now. And also we are working on a catalog of applicable connection techniques.
Okay. Thank you very much, Matthias.
You're welcome.
Okay, so let's continue. So the next presentation I will be joined by Henrik Danielsson from Lund University.
Yes, thank you, Boris. Let's see if we can get the presentation. Yes, thank you very much. Yes, so my name is Henrik Danielsson. I'm from Lund University, and I will talk a little bit about the work packages dealing with components and joints and the seismic behavior. So the overview of these work packages and a lot of other parts of our project has been can be summarized in some aspects, at least here, with the main aim as development of reliable models for prediction of load-bearing capacity and stiffness of components, joints, and also structures or buildings. And the activities presented here now in our work packages relate to theoretical work, mostly modeling using the finite element method, and also some experimental work, mechanical testing. And we'll give a few examples during this part of the presentation. First about in-plane shear loading, notches in CLT, and as you see here below, Boris will then mention something about connections, and finally something about the seismic design. But starting with in-plane shear loading, this can be either as pure in-plane shear loading or at beam loading conditions. And for these load cases, we could have several different failure modes, and we have mostly focused on the failure mode in the crossing areas between the laminations of different layers, where we can have relative translation and relative rotation between the laminations. So our work here has consisted of development of a consistent or uniform design approach for both these cases, and we've conducted experimental tests, which I'll show in the next slides here. So the tests were carried out at the laboratory in Zag in Slovenia, and we studied basically two parameters. Since we had all beams were of the same gross cross-section area, but we studied the influence of different lamination widths, 100 millimeter and 150 millimeters. And for both these lamination widths, we tested different element layups in terms of the ratio between the external and internal longitudinal layers. I'll just show here an example of test results and some comments relating to these. The test series were basically quite similar in a lot of respects. For example, that we found this initial linear response. And after that, we found a phase of a decreasing stiffness and eventually a final failure, which was more or less in bending. And here's a short video showing the strains from DIC measurements and showing how this gradual decrease in stiffness is related to the damage and failure over the crossing areas, which eventually leads to these beams with 6 laminations, first acting as one beam, but eventually acting more or less as 6 separate beams, which are then bent off. These results are not yet fully analyzed and are also yet to be published. And this is just a picture of the end face of the beam, where you can see this fracture over the crossing areas between the laminations. Next topic is notches in CLT, and notches like this, of course, geometric discontinuity like this introduce large perpendicular to grain and shear stresses, and it may lead to crack initiation and propagation, and is typically related to a significant reduction of the load-bearing capacity. These notches are still, however, used in practice, since there is often a simple way to introduce joints between elements, or as we see here, end notch supports, or half-and-half joints between floor elements, and some screwed connections could also be computationally considered as an equivalent notch. So here, in terms of modeling, we've studied some approaches based on fracture mechanics. As Erik mentioned previously, this has been a lot of his work. And we've studied a number of different approaches based on fracture mechanics. The first one could be an analytical model based on beam theory, which would then give a closed-form expression for the crack load. And this approach is similar or consistent with the Eurocode 5 approach presented a long time ago by Professor Per-Johan Gustafsson, which is now included in the Eurocode 5 for timber and glulam beams, but could be applied in a fairly consistent manner also for CLT. And we also studied structural elements and some different approaches using 2D continuum finite elements. Also here, we've conducted a number of tests on CLT plates, or actually more narrow CLT beams with notches at the supports. And we've here studied a number of different geometry parameters, the beam orientation, the notch length, and the notch height, since the height of the notch and especially the placement of the notch corner with respect to the different layers influence the load-bearing capacity. So with that, I'll leave the floor to Boris again.
Okay, so I am sure that most of you had a walk yesterday and a tour around the Sara building. And with this high-rise building, such as Sara, we also get a high capacity demand of structural connections. And in our project, we were interested in whether these high load-bearing connections cause the local failure of the CLT as a durable material itself. So we tested different CLTs, different CLT layups with different widths, orientation of the laminations with different screw length. And as you can see here, we turned up also with the brittle failure of CLT. So there are several possible failure modes, which are up here, and I invite you to look at the specimens afterwards. So it was we could see that also, although we have the cross-layered layers, we could reach this brittle failure of CLT. Then there was a lot discussed today with the project DynaTTB about eigenmodes, eigenfrequencies with the lateral stability under wind loads. Well, in our project, then we focused on the earthquake load also as one of the lateral loads possible. And especially here for high-rise buildings, we focused on the nonlinear response and proposed a simple model, which we could then use on earthquake regions and for high-rise buildings to assess and have a more exact result. And how did we calibrate, or how did we validate these numerical models? Is by firstly performed tests. And in this special case, we had tests on CLT walls with insulation, so with insulation bedding, and without the insulation bedding. And the result was that we reach a much lower stiffness with the sound insulated CLT walls, but we have a comparable load-bearing capacity. So we used first this experimental data to calibrate our models and to have a more exact result. So with this, I will conclude my presentation and going to our last part. So my mic stopped working, okay. I would like to invite our associate partners on stage. But first, we have a question for you. So in this next panel, we will discuss what do you think are the most important topics for future research with CLT. So please take your phones and again use the Mentimeter and tell us what you think we should do in the future or you should do in the future, and it can be related to the topics that we already did or the ones you feel are the most appropriate, and we will see it then on the word cloud. But while you do it, please, I will invite on stage a diverse group of our associated partners. So first, architects. It's Daniel Asp from White Architects. Please come. And Pai Ekblom from Gaia Architecture. And then we have also two structural engineers, and it's Thomas Demschner from Stora Enso. And again, Patrice Goudenou from Swedish Wood. And since we're dealing with future topics of research, I would like to again invite Professor Winter, because he is involved in the standardization process as the chairman. Okay, we already have some results that we could comment then later. But I would first be interested in which of the topics or results that you have seen now in this last hour could you use in your daily practice? So what is the...
I can start. I think from an architectural point of view, I think it's very interesting with this multifunctional CLT, which feels like the second generation of CLT, and how we can use our production methods and fully use the potential in that, and how we can include other functions into the structures that we have.
Yes, not only thermal activation, also other multifunctionality. Pai, do you have anything to add?
Not really. No, but I'm very curious in following this project and see how we can implement it in the architectural field, and I also see a lot of more innovative potential in this field of CLT and in the field of timber in general, but that is applicable to CLT as well.
Okay, and from structural engineering point of view, are there any?
Well, it was actually a very good survey. I liked it a lot, and I think you know, this looking at these questionnaires, the questions came from you, Stefan. The questions that were asked to
designers.
To designers.
Yeah, our group created these questions. Yeah,
yes. I mean, this really reflects the knowledge of the designers and of those who use our materials. And it reflects that there are certain knowledge gaps. And if we can fill these knowledge gaps as soon as possible by disseminating all that knowledge and by spreading it, I think this would be a very important first step.
Okay. Then maybe I have one more question, is because our proposal was written in 2018. Do you have any feedback on which topics maybe have gained more importance since then? Is there anything that wasn't that important 5 years ago or 4 years ago? Is something...
Well, importance, I think the material efficiency is, we see it also here reflected in Menti. I think one of your first slides that you were showing gave the same result. For us as the manufacturers, the efficiency really becomes key because of availability of material, because of the price of material, because of the quality of the available material due to several factors, due to climate change, etc., increasing demand. This is really in the future going to be key.
I also see that the importance of forestry and resilience in our forests has been even more. I mean, we're even more aware of this, and it's really urgent with storms and climate effects and so on. So I think that has been even more accurate the past years, and I think that even in the CLT, I hope that we might see more hardwood, for example, to be able to have more diverse forestry with higher resilience.
So the use of hardwood in our structures as well.
Yes.
We're on it.
Sorry?
We're on it.
Yeah.
Yeah, we also started research with that, of course. So, okay, we have started with this, but then if we have to make a choice, if maybe Patrice, if you were given 1 million euros to spend on research, what you would spend it on?
Well, as a representative of an industry association, one of my tasks is to help spread the knowledge about, for instance, structural design methods. So I think one of the things I will look forward to is spreading the information, the outcome from this work in design guidelines for researchers, and then going further with the multifunctional CLT that you presented earlier. I think there is more to be done there before you can really make it to commercial products. And I have some representative from Swedish CLT manufacturers here. We were meeting yesterday. One of the things we are discussing is the need of putting the information, make the information available out now for engineers, practitioners. I sit on our hotline and I often get questions like point load. Someone calls, I have designed something about the point load. Can you tell me if this is accurate enough? Or I have holes in my floors or slabs, and I have used calculatis or CLT design or something, is it reliable? And I say, I cannot give you that assurance. So really what you have done here is something that needs to be spread out as quick as soon as
we still have some time till October, so our project was extended.
Oh, and October, then I'm very happy.
Yes, so we will work on it.
Boris, to answer your question about the 1 million, I would like to invest part of this money definitely not only in improving design rules, but also improving execution rules. If I'm looking sometimes to building sites with CLT, and I'm looking especially not to white architecture, because I know you are experienced with, but I'm looking to the side of the architects or of those who are managing sites, I very often see that CLT is handled like prefab concrete. Yeah, not protected at all during erection. Water is going inside, and then you need a long time for drying out period, etc., etc. I think we should also invest in future more in execution rules, more in protection on site. We are not able to build every time like our Swedish colleagues do very often, a tent above a home we erect. That's not possible, especially not in inner cities, for example, when we are filling gaps or things like that. So we have to train at this point. And my second, the rest I would like to invest.
So it's 2 million.
Again, in a technology coming from concrete.
Yeah.
Pre-stressing. I think there is a very big possibility in improve further pre-stressing also of timber elements, especially of CLT with cavities in it. Hybrids combined from hardwood, I agree fully what you said. Combined from hardwood and softwood, for example, then you have cavities in it. We can use that for pre-stressing, things like that. There's a lot to do. And 1 million is not enough.
It's not enough, right? Yeah, but it's connected to one of the most answers with moisture. And let's now open the floor for you also, so we can answer. Are there any questions about our work? And Henrik will give the microphone, and I cannot see well if there are any raised hands. Okay, there's one here.
Hi, Ed Suddy from BRE. I just wondered about the insurance and the loan community. Buildings are assets. They're always parts of financial portfolios. And whether you foresee any particular challenges that could be resolved for CLT particularly in terms of, well, we've spoken about design guidance, we've spoken about perhaps gaps in execution on site, for instance. Do you have any sort of concerns or thoughts on that?
You mean, if I got your question right, that insurance of buildings could be difficult or something like that?
Yes, and they're always part of a financial asset. So it's a portfolio of buildings. It might be a hotel chain. It might be an investment portfolio of retail outlets. And that's all based on an understanding of the performance of that building, its future-proofing, its climate resilience, you know, lots of different factors.
Yeah, I can only talk from my experience building for those guys from time to time in projects. I think they weigh much more nowadays the sustainability. It's carbon storage, CO2 sink. This is also for them an argument today. They know that the normal lifetime of the building is the same compared to others. Of course, there you have sometimes discussions about fire safety up to now, and you sometimes have discussions about moisture safety. But investors in general, you are able to convince if you have a good design. Good architecture is very important. And if you are able to prove that you have a good design team in total, so that you have experienced engineers, experienced building services engineers, experienced companies who are building, And then that's my experience. Probably our colleague from Store Enzo could also add to this. I don't have the impression at the moment that that investors are not willing to avoid also in mass timber or timber constructions.
I can add some more comments on that as well from our experience, from our projects. We have several large-scale timber projects, and I think all of them that are successful is because we have a good collaboration with the investors and with the clients. And they come with a clear view that they want to build as much as possible in wood. And that also shows later when the projects they are finished, they can rent out the building for more money, and none of them have any problems in getting people interested in that, because also the people who are going to rent the building, they often want this sustainability brand on their company. So I think from an investment point of view, as long as they are interested in building in wood, I think we haven't experienced that it's a big problem. There is a problem sometimes for other projects where it's not as defined that it should be in timber. And then when you compare timber with concrete, for example, the problem I think then is that you compare a concrete building and a timber building built as a concrete building. And then it's harder to argue that you should build it in timber. But if you build a timber building as you should build with timber, I think that's important to get the client and get a successful result as well. So.
I see here two aspects in the value of that building, of that timber building. One of it being the reputation. So if you are in that sustainable building, then this is adding to the value, certainly. And the other thing is how can you capture this value, or how can you put the price tag to that value? That would be, in many cases, meanwhile, the sustainability certifications. Yeah, you name them. It's BREEAM, it's LEED, etc. And if you have a certain ranking within this sustainability label, that is certainly then also an increase in the value, something that you can sell, because if any large corporation, let it be IBM or whoever, if they say, hey, we have our offices only located in buildings that have BREEAM standard. Well, I'm not that familiar with the individual grades, but let it be platinum or 5-star or whatever, that the highest, that is absolutely an asset. Yeah.
Thank you. Are there any more questions? There is one, I see.
This is a technical question for the presenters before.
Yeah.
What kind of glue are you using for your research? Are you investigating different types, or are you going for one type?
I think that most of the CLT that we tested was of one type of polyurethane adhesive. So, and also with the multifunctional CLT, it was the same, right? Yes. So, if we continue with the future research, of course, we will in the future have to consider also bio-based adhesives. Already we mentioned, and I think Eric had a good keyword, a CLT 2.0. So this multifunctional CLT or CLT with different bio-based adhesives could be named the CLT 2.0, so the second generation as well. Any other questions?
No more questions.
No more.
Sorry.
Can I add one thing to the resource efficiency? That is just that we don't get stuck in the CLT technique when being efficient with the material. I think we have to combine different timber techniques and taking care of for example, timber dust in masonite instead of burning it for biofuel and so on. So there are a lot of things to do.
Okay. So thank you for listening. And with the closing line, I would like to thank also our financiers of the project and this good opportunity for our work to be done. It wouldn't be possible without that, and we're also looking forward to future calls and to be able to continue and do some of the, oh, they're not there anymore, some of the topics that are on the screen. Yeah. So thank you.